All right, everyone, this is lecture 6.1, where we're going to begin talking about aqueous solutions. All right, couple things to discuss in this video. First is we're going to introduce a little bit of terminology, just a couple of simple new terms, and then we're going to talk about what it means for something to be dissolved in water, and we're going to look specifically at electrolytes, non-electrolytes, and weak electrolytes. All right, so the terminology first. Solution is a term that we're all familiar with, and we kind of know what a solution means. There is a special chemistry definition of this, which is slightly different than what you might be thinking of. Chemistry definition says that a solution is a homogeneous mixture of two or more components with a variable composition. Variable composition is important to distinguish between mixtures and compounds. Remember, compounds have a constant composition. Mixtures have variable compositions, and a solution is a type of mixture. So it's a homogeneous mixture of two or more components, and it's often, but not always, a liquid. When we think of a solution, we usually think of liquid solutions. Most of the solutions that we encounter in the lab are liquid solutions. Nearly all of the solutions you come across are going to be liquids. However, based on this definition here, right, that definition is a bit broader, and so that does actually include mixtures of gases or even mixtures of solids. So you can have solid solutions or gaseous solutions. All right. There are two primary parts to a solution. The first part is the solvent, and the solvent is just the major component in a solution. That's what makes up most of the bulk of the solution. Again, if you think about solutions, you're usually thinking about liquid solutions. So the solvent is usually that liquid that everything is dissolved in, and for us, that's usually water. Right? The other part is the solute, and the solute is whatever is dissolved in the solvent. The solute is the minor component. Okay? And a solution can have multiple solutes. If you go in the lab, you can take sodium chloride, dissolve it in water, and you'll have a very simple solution where the water is the solvent and the sodium chloride is the solvent. But you can have much more complicated solutions like apple juice or something where the solvent is going to be water again, but there are many solutes. There are all of the flavored molecules that come from the apple. There's sugar, and there's malic acid. There's a whole bunch of other things that will form the solution of apple juice. Okay, so you've got one solvent. You can have one or more than one solvent. Excuse me. You got one solvent. You can have one or more solutes. You can have multiple solutes dissolved in that solvent. All right. So as I said, solutions are usually liquids, but not always. One example, seawater is a common example of a solution. The bulk of seawater, of course, is water, so that's the solvent. Seawater has multiple solutes in it, sodium chloride, potassium chloride, magnesium sulfate, and a lot of other things. I'll mention another one here. Fish got to breathe, and so there's actually oxygen dissolved in the water as well. You can have gases dissolved in a liquid solution. All right. Tea is another good example. Again, bulk of the tea is just water, and the solutes include tannins, which are all of those sort of colored molecules that leach out of the tea leaves to give tea its kind of brown color. Tannins is not a molecule, but it's a class of molecule. There are many, many different tannin type molecules that will leach out of those tea leaves. There's also caffeine And if you want to have sweet tea, you can add some sugar to that. So you can have multiple different solutes. All right. As I mentioned, some solutions can be gases. Right? If you follow the strict chemical definition of a solution, it's just a homogeneous mixture of many components, right? And so air actually qualifies as a gas phase solution. The major component in air is nitrogen, because that's about 78% of air is nitrogen. And then the other components are oxygen, carbon dioxide, methane, a whole bunch of other things. And I'll mention this one here too. There's usually a fair bit of water vapor in the air. And so water is something we normally think of as a liquid, but you can have a few gas phase water molecules in that mixture. Okay, so my reason for pointing that out is that you can have things that are typically liquids in a gas solution, and you can have things that are gases in a liquid solution. And as I mentioned, you can also have solid solutions. So brass is a mixture of copper and zinc. Copper is the major component, so that would be considered the solvent, and zinc is a minor component, usually about maybe 10 to 20%, so that would be considered the solute, and those two things together form a solid, which is brass. Okay. All right, so we're going to be focusing mostly on aqueous solutions. So I want to talk a little bit about what it means for something to be dissolved in water. Okay. And water is an important molecule. I mean, obviously it's important because it's around everywhere, but it has special properties. Okay. Water molecule is bent like that. So it's kind of shaped like that. And we haven't talked about the structures of molecules very much lately, but there so far. But I will say there's an important thing about water molecule, and that is that the electrons in this molecule are not evenly distributed. Because the oxygen is more electronegative than the hydrogens, the electrons tend to be distributed more around the oxygen and less around the hydrogen. And that makes the oxygen end of the molecule slightly, I'm not going to use that symbol, let's just use this. That makes the oxygen end of the molecule slightly negative and the hydrogen end of the molecule slightly positive. And when you have a molecule like this that has a positive end and a negative end, we could kind of designate it like this. Okay, that just means that it's a molecule and one end of it is slightly more positive and one end is slightly more negative. And we have a molecule like that, we say that it is a polar molecule. Okay, it's got a positive part and a negative part. And that's important because when you dissolve something in water, the positive part of the water molecule can be attracted to some solutes, and the negative part can be attracted to other solutes. So the things that dissolve in the water, they're not just floating around by themselves. The solute molecules in the water are interacting with the positive and negative parts of the water molecule. Okay. So the way we indicate that with a chemical equation take something simple like sodium chloride. I don't think we've used this symbol either. But you can write something in a chemical reaction, you can write something over the arrow to indicate something about the process or the conditions. When you've got something that's important to the reaction, but it's not actually a reactant. It doesn't really take part in the reaction. You can indicate that over the top of the arrow. All right, so to indicate sodium chloride dissolving, you can write this like this, and this little AQ in parentheses stands for aqueous. Which just means dissolved in water. Okay. And so when you see aqueous, that means that that substance is in water and it's interacting with those water molecules also. So this sodium chloride, we'll look at sodium chloride in more depth in just a second. This sodium chloride over here is going to be a little bit different than the sodium chloride over here, because here this is dissolved in water and interacting with those water molecules. All right. Okay, so I'm going to look at what species do when they dissolve in a little bit more depth. And let's take sodium chloride, for example. Okay. Sodium chloride, we wrote this like this a minute ago. Wrote it like that to indicate that it's dissolving in water. And that's fine. That's kind of a nice shorthand way of indicating that the sodium chloride is dissolving. But what's really happening is when the sodium chloride dissolves, it starts like this. Sodium chloride, of course, is an ionic compound, so it exists as kind of an array of alternating positive and negative ions. Right, so you've got like this block. Might be a fairly small crystal, but even a small crystal is going to have millions of ions in it. And then when you dissolve it in water, the water interacts with this, and these ions are actually going to separate so that the sodium ions all of the water molecules surround the sodium so that the oxygen part, or the negative part of the water molecule, is pointing toward the sodium. The positive charge on the sodium attracts the negative end of the water molecules. Okay. And so the sodium ion is actually surrounded by kind of a coating or a sheath of water molecules that are all somewhat strongly attracted. It's definitely not as strong as a covalent bond, but there's a fairly strong attraction here between the sodium ion and these water molecules that are surrounding it. Right. And so we can describe this here as, call this a solvated, that looks like a star, I didn't mean a star. An aqueous sodium ion. Okay. And the chloride is going to do the same thing. Chloride ions get into solution, and the water molecules are going to interact with the chloride, except for now it's going to be the positive end of the water molecules that are attracted to the chloride. So we got this little attractive forces there. And so again, that chloride ion is surrounded by sort of a coating of water molecules that envelop that chloride anion. And we can indicate that like that. So an aqueous chloride ion. Now the behavior of these guys here, the sodium ion and the chloride ion, is going to be very different from the behavior of this crystal here. Okay? As you can see, if you just look at them on the microscopic level, the microscopic representation, they're very, very different. This is a large group of ions all clustered together with alternating charges, and these are individual ions, each surrounded by a sheath of water molecules. All right, so let's take this equation here and rewrite it in a way that's a little bit more correct. The equation that I have up there in green is fine. I wouldn't really say it's incorrect necessarily, but it's a shorthand. Right? The truth is, I guess we can say it this way. Sodium chloride aqueous, this here, this does not actually exist. There's no such thing as dissolved sodium chloride molecules in the solution. Right? The solution doesn't actually contain any sodium chlorides. It contains sodium ions and chloride ions, but it doesn't contain any sodium chloride per se. So a more accurate way of describing this reaction would be to write it this way. Okay. So this is two ways of saying the same thing. In both cases, you're just saying sodium chloride dissolves in water to form aqueous sodium chloride. This one up here, this is fine 9 times out of 10. It's just a shorthand way of saying this down here, which is a little bit more complete and a little bit more accurate, making the point that when sodium chloride dissolves, it forms sodium ions and chloride ions. Okay, all right. So you can see from the title here, we're going to talk about electrolytes. And what we were just looking at is an example of an electrolyte. All right, and normally we just call these species electrolytes, but we will later on be talking about a group of molecules called weak electrolytes. So we could distinguish these if we want by calling these strong electrolytes. If you just say electrolyte, it implies a strong electrolyte. So the term electrolyte is fine, but you could also say strong electrolyte. These look like P's sometimes. All right. So an electrolyte is a species that dissolves in water. There are two parts of this that are important. Species that dissolves in water, and when it dissolves in water, it produces solvated ions. Okay, so there's two parts to that, and sodium chloride that we just saw is a perfect example, kind of the stereotypical perfect example of a strong electrolyte. All right. It's important to recognize which species are going to be strong electrolytes, because you want to be able to describe what they're actually doing in solution, and you want to know if in solution they exist as these solvated ions or if they exist in some other form. Okay, so we need to know what are strong electrolytes, and there are two groups of strong electrolytes. One of them are things like sodium chloride. So give me just a minute to get this cleaned up over here. All right, so the first group are soluble ionic species like sodium chloride. You'll see in the next video, we'll have a list of rules for determining which things are soluble or insoluble, so you'll know which ionic species are soluble. Okay, so electrolytes are soluble ionic species, like sodium chloride, and when these species dissolve in water, they make these ions. Okay? But it's important to recognize that when they form these ions, the ions themselves don't break apart. Right? If you have a polyatomic ion, something like, let's say, potassium sulfate, that's also soluble. Right? You put that in water, that's going to break up into ions. Okay, but this here, right, this sulfate ion doesn't break apart into sulfurs and oxygens. This sulfate is one unit, so and that unit maintains its integrity. So you get a sulfate ion. Okay, and then this part here. Okay, now this isn't going to form K2, right? Because K2 would indicate two potassiums tied together, and that's not what this is. Remember back to when we were doing nomenclature, right? This formula here, K2SO4, means that there's a sulfate ion with a -2 charge, and that it's balanced out by 2 potassium ions. Okay, so when this thing dissolves in water and breaks up into ions, you're going to get 1 sulfate, which we have here, and you're going to get 2 potassiums. Okay. So when potassium sulfate dissolves, you get 2 potassium ions and 1 sulfate ion. You could have something like iron nitrite. I'll say iron nitrate. Okay. And that's going to break up into ions. So you're going to get an iron ion. Okay. And you need to know what the charge is for this iron. So you need to do, just as we did when we were doing nomenclature, you have to kind of take this and reverse engineer it. Right? Each one of these nitrates is a -1 ion, and there are 3 of them, so that means the iron must be a +3. Okay. So you're going to get iron 3+, and then you're also going to get nitrates. Okay. And again, the nitrates don't break apart. Right? The nitrates themselves maintain their integrity. Doesn't break apart into nitrogens and oxygens. Okay? And each one of these molecules, right, or each iron nitrate species contains 1 iron and 3 nitrates. So when it breaks apart, it's going to give you 1 iron and 3 nitrates. I doodled over this a little bit, but I hope you can see the reaction there. Iron nitrate, solid, dissolving in water to form 1 iron 3+ ion and 3 nitrate ions. Okay. All right. So that's the first group of strong electrolytes. Okay, that is, strong electrolytes are things which dissolve in water to produce ions. The first group are soluble ionic compounds. And I mentioned in the next video, you'll get a bunch of rules for determining which things are soluble. All right. The other group of strong electrolytes are the strong acids. Okay? And there are 7 common strong acids. And these come up a lot, so you really need to know these. Fortunately, they're pretty easy to remember. You might make yourself a flashcard. There are some other strong acids that exist, but of common acids, things you're likely to run into, there are only 7 which are considered strong. The first 3 are binary acids of the halogens. So if you look over there in group 7, you've got fluorine, chlorine, bromine, and iodine. 3 of those are strong acids: hydrochloric acid, hydrobromic acid, and hydroiodic acid. Okay? It's important to remember, even though it's the same group and it looks like it ought to belong there, HF is not a strong acid. Okay? So just these 3, hydrochloric, hydrobromic, and hydroiodic. Okay? The next 2 are 2 that are very common. You've definitely heard of these, and so it's easy to remember that they are strong acids. And that's nitric acid and sulfuric acid. And then 2 more that you probably would not have guessed, and that is chloric acid and perchloric acid. All right, so you should know that list. And this is going to be important, particularly in the second part of the course when we talk about acid and base chemistry. You'll need to determine whether things are strong acids or weak acids. And usually the way you can tell something is a weak acid is if it's an acid and it's not on this list. Right? So being able to group everything between strong acids and weak acids really comes down to memorizing this list of 7 strong acids. So you want to start working on that. All right. So what do we mean by these strong acids? I apologize that jumped ahead to the next slide. I'll finish it. We're still talking about the strong electrolytes. For the strong electrolytes, strong acids, the way they behave as electrolytes is if you have something like HCl, which is normally gas, you dissolve that in water, it's going to dissolve and it's going to give you ions of H plus and Cl minus. Okay, just like the solid ionic things like sodium chloride, magnesium bromide, things like that. Nitric acid, same thing. Dissolve this in water. You can get H plus and nitrate ions. Okay. Again, the ions themselves maintain their integrity, but they split up from the cation. And for the sake for the, we're talking about strong acids, that cation is always going to be H plus. All right. So this reaction will be played out for all of the strong acids, which are strong electrolytes. All right. So now my page jumped ahead a little bit early. But so now we'll talk about the non-electrolytes. All right, if you remember the definition of electrolytes, we said there were 2 parts to that definition. Electrolytes were things that, 1, dissolved in water, and 2, split apart into ions. So non-electrolytes, not surprising, there are 2 types. There are those that don't dissolve, right? If you don't dissolve in water, then you can't act like an electrolyte. And so these are things like iron hydroxide. This is insoluble. So if you put this in water, iron hydroxide is kind of a reddish brown powder. So if you put that in water, you end up with a wet orange brown powder. It doesn't dissolve, it doesn't do anything. Okay, and so because it doesn't dissolve, it can't break up into ions. Okay, so any of the ionic compounds that are insoluble are going to be non-electrolytes. Okay. The other group are things that are soluble but aren't composed of ions. So these are soluble covalent compounds, and most of these are organic compounds. So things like methanol. So methanol is a liquid. Dissolve that in water. Okay. Then all of the methanol molecules will dissolve. They all become surrounded by water molecules. They get that sort of sheath of water molecules around them, right? But they don't break up into ions because the molecule itself is not an ionic compound. Okay? You can recognize these typically. A simple sugar molecule would be another example. You can recognize these type because they're almost always organic molecules. I can't think of any other examples of soluble things that aren't inorganic soluble things that aren't organic molecules. So I would just look for this combination of carbon, hydrogen, and oxygen. Basically, if you remember the list of ions that we had to remember a little while back ago, if you don't see any of those ions in here, then it's a covalent compound. Okay, and if it's soluble, it's going to be a non-electrolyte. It dissolves, but it doesn't produce ions. Then we've also got weak electrolytes, and almost all of the weak electrolytes are weak acids. And as I said a little bit ago, how do you recognize a weak acid? A weak acid is anything that's an acid but isn't in that list of 7 strong acids. Okay. So for example, HF, hydrofluoric acid, we said that that was, actually let me write this. Let's say we've got HF that's dissolved in solution. And when HF dissolves, it breaks apart into hydrogen ions and fluoride ions. So in that sense, it's acting like an electrolyte. But the difference is in a weak electrolyte, when it dissolves in water and breaks apart into ions, those two ions rapidly recombine to reform the original acid. So you've actually got two processes happening at the same time. You've got this happening where the HF breaks apart to form ions, just like a regular electrolyte, but you've also got the recombination reaction going to reform the original molecule. And for something to be considered a weak electrolyte, what that means is that the overwhelming majority of the molecules at any particular point are in this form over here. The amount is going to depend on the acid and the temperature and the concentration, but a typical amount would be something like 95%. So 95% of the hydrofluoric acid is in this form, and only about 5% is in this form. So it's forming some soluble ions, but not very many. Okay. Another example would be acetic acid. And how do you know acetic acid is a weak acid? Because it wasn't on the list of strong acids. It's just that simple. All right. So acetic acid, when you put it in water, it breaks apart and it gives you hydrogen ions, okay, and acetate ions. Okay. And just like in all the other cases, the acetate maintains its integrity, doesn't break apart into carbon, hydrogen, and oxygen. The acetates remain together, okay, but it breaks apart into hydrogen and acetate. Then these two in solution have a tendency to recombine, so that at any point, most of the acetic acid molecules are in this form. Again, probably about 95% in most cases, and a minority of the acetic acid molecules are in this dissociated form in which they're broken apart into ions. All right, so we looked at terminology, really just three terms: solution, solvent, and solute. Remember, the solvent is the major part of the solution. The solute is the minor component or minor components if you have multiple components in your solution. We looked at aqueous solutions. We looked at the fact that water is a polar molecule, and so it's going to interact with things as they dissolve. And we indicate something that's dissolved this AQ, meaning that it's surrounded by water molecules. And if you have something that's an electrolyte, that would more accurately be indicated by showing the individual ions, each of them surrounded by water molecules. So we got AQ on there. And we talked about electrolytes, non-electrolytes, and weak electrolytes. Electrolytes are things that dissolve in water, and when they dissolve, they dissociate into ions. Non-electrolytes are things that either don't dissolve because they're insoluble, or they don't release ions because they're not ionic. Okay? And then we looked at weak electrolytes, which are kind of in between those. These are things that act sort of like electrolytes, but they recombine so quickly that the majority of the components are in an unionized form at any particular time. All right, okay, that's it for this video. Thanks for listening, and I will see you next time.